Thank you very much, Magnus. So, hello, my name is Stella Biderman. I am one of the lead scientists at EleutherAI, which, for anyone who doesn't know, is a online research organization, which I guess takes us to the first slide. So we are literally a Discord channel where people come and they talk about AI research, especially transformers and language models. And it's a place where people collaborate and perform research. We've been around for close to 2 years now. And over the past 2 years, we've been able to kind of both produce some, I think, very interesting research, as well as get some support from funding institutions. So we're a Discord channel that actually has like GPUs and stuff that we can lend out to people. So we try to organize open source research. One of our big focuses is on making this kind of research more accessible, more public, and more collaborative. So I'll start off by saying a little bit about us and what we're up to, and then I will go into kind of the 20 billion parameter model we just released. So our origin story is somewhat amusing. So Connor Leahy is a AI researcher in Germany. I think he's actually moving to the UK in the near future, but at the time, at least, he was in Germany. And for those of you who don't have like archive links memorized, this is the archive link to the Language Models Are Few-Shot Learners paper, the paper announcing GPT-3. And Connor was in a Discord chat about AI, and he said, "Hey, let's do this." And another one of our founders, Leo Gao, said, "Yeah, that sounds like fun." And so they made a Discord server and they started talking about what it would take to train their own copy of GPT-3. And that's how we got started. So like I said, our community is organized via Discord. We're very excited and passionate about transparent research and being community driven. So almost all of the work that we do and almost everything that goes on at EleutherAI is accessible to anyone. In the sense that you can literally like drop into our research discussions. You can read about our interim results. You can, when we present internally, that's through our public Discord. You can just drop by and listen to what we're up to. And a lot of people do. We have members from academia. We have people from various industry groups who drop in and talk about research and just learn about what we get up to. Obviously, not literally everything is publicly accessible, because I'm going to start talking about training a model on 96 A100 GPUs, and we don't like leave the passwords to access those in public Discord servers. But in terms of the research, one of really our big focuses is developing things in public, because in industry, there's a very big focus on proprietary nature of code, of models, and of data. And there are a variety of reasons why that is put forward as an acceptable model. And we think that, and one of them is that there's a prominent attitude that you can't do research in public because of people stealing your ideas. You can't do research in public for some logistical reasons that we don't particularly agree with, and we're kind of a counterexample to that. It's community driven, and like I said, anyone can join. You're welcome to join if you don't want to literally like co-author a paper with me. You're welcome to just read about what we're up to. There's a lot of discussion of state-of-the-art research, and we have some regular events. So right now we have an interpretability reading group that happens every other week, where we bring in people to give presentations about recent papers and stuff that excites us. So there's a lot going on, and I'm gonna figure out we're gonna send these slides out after my talk, and there'll be a link at the end of the slides to join our Discord if you're interested. So the big thing that we focus on is language modeling. Like I said, we got started by saying, hey, it would be cool if we could replicate GPT-3. And most of our work, though not all of it nowadays, is focused on language modeling. So this is a slide from a presentation I gave at DEF CON about a year and a couple of months ago, or about 9 months ago, I should say, summer 2020. And I wanted to include it because of just how stark the progress has been. This was a mostly complete list of the publicly known large autoregressive language models. You have GPT-3. You had the then new Hyperclova, which is a Korean language model. GPT-NeoX was something that we had in the works. It actually just started training when I gave this talk. Microsoft had a model. The Big Science Research Project was working on a 13 billion parameter model, and then there were ones in the 10 billion parameter range. And now the world looks a lot different. So I actually have a spreadsheet there's a link to this in the slides, where I have been writing down and documenting all of the large language models I can find information about. So these are the 15 largest language models in the world right now. There's a little asterisk on that because a lot of companies have developed models before they've announced them or before they've shared details about them. For example, I know that people at Facebook have publicly implied that they have a GTB3 scale model, but there's no information about that that's available anywhere. So that is not included in this list, for example. But you can see almost everything on this list is very new. And Magnus mentioned at the beginning about how he's interested in bringing stuff to the Nordic countries and to the Swedish language. And one of the most stark things about this is if you look at the locations of the people who produced the work, as well as the languages that the models were done in, dominated by the United States and by English. And of the stuff that's not the US and English, it's highly dominated by China and Chinese. There is not very much representation of Swedish, of all sorts of other languages. I believe that in my entire list of all language models larger than GTB2, which is about 40 or so, there are English and Chinese are the only languages that have English and Chinese are the only languages that have multiple models trained in them. So that's, a very specific subset of people who have access to these technologies and the ability to use these technologies for problems that's interesting to them. And what I'm here to talk about today is GPT-NeoX, which is the 20 billion parameter model we recently trained. It is also, I'm very excited to say, currently the largest publicly available model in the world. We have put the weights online, though the extent to which that actually makes it accessible to people is kind of dubious, and I'll talk about that towards the end of the presentation. And we've also tried to do a lot of work about making other structures like data sets, like evaluation frameworks, more publicly available. So there are several larger language models that have been trained on either entirely or in part data that we produce, which is something I'm really excited about because I think that data accessibility is a topic that gets underrepresented in these conversations about access to technology and kind of the ability to study language models. So I want to talk a little bit about GPT-NeoX and what we did. And I want to focus on what it's like to actually train a very large language model, because that's something I think I think something that not many people have a lot of experience with, and it's something that I think is underdocumented and underrepresented in these conversations. One of my colleagues at EleutherAI recently put out Horace recently put out a blog post about the considerations that go into scaling language models in general, and kind of there's a gloss over level of conversation that people have about this, but if you want to get into training large language models, you need to have a pretty good understanding of a lot of the trade-offs involved in large-scale computing that is really not particularly represented in conversations about AI in general, which I think is really a shame, because to a large extent, these projects are engineering projects first. The lead author on the paper that we've written about our model is Sid Black. He's our lead engineer. And that's something that you see across different organizations. If you look at the GTB3 paper, the lead author is also someone who focused primarily on implementation of their models. So what is a transformer? This is kind of the standard diagram of a transformer, but I feel it's actually not a particularly good way to represent or talk about them. This is a diagram from a paper on what's called post-layer norm, a paper on layer normalization. And I think it's a much better representation of kind of how transformers work from the point of view of architecture and scaling. So our transformer looks like the one on the right. The only difference between these is the location of the layer norms, which is what this paper was about. But this is kind of what one layer looks like. You have a residual stream going down the middle here, and then you have to take the residual stream, compute some attention, and recombine. And you have to compute a feed-forward network and recombine. And so this operation together constitutes one layer of a transformer. And this is kind of the core object that we're going to talk about what it looks like to parallelize. So these models are trained on very large numbers of GPUs. We use 96 A100 GPUs. I believe I was told at some point how many GPUs the model AI Sweden just put out was trained on, but I'm blanking on that number right away. And there are kind of three main ways that you parallelize these computations across these GPUs. Because if you do it naively, you end up with very poor performance and a lot of GPUs sitting idle. So the way to look at this diagram, this is from the Zero paper, which is a optimizer put out by NVIDIA, and is kind of the starting point standard for how you go about training these models. So this diagram shows three types of parallelization. You have model parallelization. So each individual layer is too large to fit in a single GPU. So we break it up across 4 GPUs, with a quarter of the layer going here, a quarter of the layer going here, and so on into the back. And we also need to put the different layers on different GPUs. So all of these GPUs together compute one layer, and after they're done, they pass the data forward, and these GPUs compute the second layer, these GPUs compute the third layer, and that's called pipeline parallelism. And then the third kind of parallelism is data parallelism. These models are trained with very large batch sizes, in the millions of tokens, or thousands of sequence lengths, depending on how you want to measure that. And so we actually, because the models are so large, most of the memory space is taken up not by data, but by the model itself. And so in order to do all of these different, in order to do a batch size of 1 million tokens or 5 million tokens, we actually need to have multiple entire sets of the model. So in this diagram, the top and the bottom planes are complete copies of each other. This is one instance of the model, and this down here is the second instance of the model. And they're going to be running completely in parallel, and they're just going to be given different data. And then when we get to the end, we're going to average their results to kind of move along. So data parallelism is pretty straightforward. Like I said, we're going to run the model multiple sets in parallel, and average kind of the results at the end. But pipeline parallelism and model parallelism are pretty important topics I want to talk about a little bit, as far as technical content goes. So pipeline parallelism is about how you time the organization of passing a layer from one GPU to the next. So I said that these GPUs together compute one layer, and then they pass their input data to these GPUs, and these GPUs compute one layer and they pass the data along. And if you do that naively, you end up with a diagram that looks like at the top. Here you have device 0, device 1, device 2, device 3, and F for forward, B for backward. So the blank space in this diagram represents time that the GPUs are idle. So if you just compute one set of data, pass it along, and you wait until you get the back propagation, pass back, you're going to have most of your GPUs idle for a very long time. So what people do is called, so the approach of pipeline parallelism says, instead of working with all of your batch at once, you're going to break it up into what are called micro batches, and you're going to do it in quick succession. So the very first GPU is going to process some amount of data and pass it along. And while the second GPU, I guess I'll say 0th to stay in line with the indices. So 0th GPU works on some data and passes it along. And while the first GPU is working on that same data, the 0th GPU picks up its second piece of data. And so you end up being able to run each, you're able to break up this batch into 4 micro batches, and you're able to keep the GPUs running for longer. And what you end up with is that you have to compute the forward passes before you do the backward passes. So you end up with this bubble in the middle. Here it was much, much larger. And a lot of the advances in pipeline parallelism kind of focus on how can we minimize this bubble? How can we fill in these additional blank spaces? And what this comes down to is largely complicated scheduling. So ultimately, this is about timing the passing of data between GPUs, which is the most important thing. It's the thing that you have the best ability as an engineer to improve on in your model implementation. And so it's something that is really important to focus on and make sure that you're doing well. Nowadays, there are a couple frameworks that have the ability to do this for you. So we used a code base that we wrote based on Megatron Deep Speed, which is an excellent code base. There's also the FairSeek library from Facebook, or I guess Meta now, also has pipeline parallelism as an option. And there's a new group called Oslo that we've been talking to that are currently implementing what seems like a very good pipeline parallelism framework. So this is something that's starting to become available in widely available packages. You know, if you go back 2-3 years, you had to write this stuff from scratch, but thankfully the kind of base level technology at least is becoming more widely available. And then the other type of parallelism is called tensor parallelism, or it was called model parallelism in this diagram. And the idea of tensor parallelism is that our layers are too big to actually fit on a single GPU. The hidden size of GPT-NeoX is, I want to say 20,000. I should have double checked this before I gave this talk, but I forgot to. It's very, very large. It's a very large hidden size, and so the layers themselves don't fit. Now, fortunately, attention is extremely parallelizable. You can actually just take attention and break it up, and that's what this diagram is showing. If you have your key, your query, your key, and your value matrices, you can just break them up, like the first half and the second half. And you put the first half on one GPU, you put the second half on another GPU, you run them independently, and then you eventually concatenate them to get the answer. And this shouldn't be too surprising, because the reason it's called multi-headed attention, is because we are doing it multiple times. Each different head works independently, and the results are concatenated at the end. And so if you think about it, really what most of tensor parallelism is about is going back to the individual head level and saying, okay, my set of GPUs is going to work on one head or two heads, as opposed to all 8 or all 16 that the model uses in its entirety. Cool. So now I'm going to talk a little bit about our model and how we optimize it, and kind of how we trained it and where we went from there. So this is a diagram of what a node in our framework looks like. And most of these diagrams can be found in the preprint that we wrote about the model. It's available on our website, and there's going to be a link in the slides. And in the near future, fingers crossed, we're going to update some details and get a copy posted on archive. So I said that we train 96 A100s, but it's not just 96 GPUs sitting around. They're organized into 12 nodes of 8. And this is probably the most important thing to understand in terms of training large language models. Your different GPUs are not interchangeable. You have better connections within a node than you do in between nodes. And this is true whether it's on a workstation or whether it's in a data center. You're going to have much better, in our case, we use NVLink mesh. You're going to have much better connection within a single node than you're going to have connecting to the other nodes. And this is really important because it governs how you're able to set up your models, because certain kinds of communication happen more frequently than others, and the blocking on communication is kind of the biggest source of downtime when you're running these models, and the place where there's the most opportunity for error. So if we go look at the layout of the GPUs, what we're looking at here is 4 nodes of 8 GPUs each, which is kind of your standard layout, and 0, 1, 2, 3, and you can't really see them, but 4, 5, 6, 7, and 8. 4, 5, 6, and 7. The left column is all one node, and this column is all one node, and this column is one node, and this column is one node. And the way that lines up with the different kinds of parallelism is extremely important. So the key feature here is that we never revisit nodes. We have our first node doing our first layer. We have our second node doing our second layer. They don't have to line up one to one. So we used they don't have to line up one to one. You can have 2 nodes computing a layer, or you could have a node computing 2 layers. But kind of for simplicity, I'll pretend they do. What's the key thing here, though, is that you're going to be computing all reduces within a node, within a layer, much more frequently than you're going to be doing it in between layers. So if we go look at the tensor parallelism, you need to compute an all reduce here to bring these different components together. And you need to compute this all reduce a lot. If this is scheduled across node boundaries, it's going to be extremely slow. You can get a 5 to 10 times speed up usually in communication within a node versus across a node. And so because you're going to be doing this kind of all reduce extremely frequently, it's really important that it happens within a single node before you go and use the lower quality interconnects between nodes. And then we have our pipeline where we're passing from node to node, and then we propagate backwards. And the other kind of key thing here is that despite being data parallel, these GPUs are, the multiple data parallel replicas are running on the same node. And you can run them on the same node, or you can run them on entirely separate sets of nodes, but you really can't mix them up. So it's really important that in terms of using your bandwidth most efficiently and using your communication most efficiently, that you don't revisit nodes that you've previously accessed. So after the data moves off of node 1, the data never comes back to node 1 until you're doing back propagation all the way back there. And that's another huge pitfall that you can easily get trapped in. Another really important component of training these large language models is data. So we compiled our own data set about 1.5 years ago when we started this enterprise, which we called the pile. It is, depending on your point of view, either 800 gigabytes of text or about 1.25 terabytes of text. The reason for that is that at the time we did the research, at the time we built this data set, the accepted best practice was that you upsample data that you wanted to, that you thought was more important and you wanted to see more frequently. And so we have 800 gigabytes of text, but we've upsampled it substantially. So we end up with about 1.2 terabytes of text. Whether this is actually the best approach has been called into question by some recent research. And I think that's really awesome. And I think it's great that people are looking into this. I would, but for kind of our purposes, this is the data set we have to work with. It's unfortunately time consuming and expensive to produce new data sets. And so right now we don't have particular plans to deduplicate and make a new pile that's, 1.5 terabytes of unduplicated text. But it's definitely something to keep in mind that whether the approach we took about 2 years ago is still considered the best approach is something that is, I'll say it's been called into question, though it seems to be the approach the majority of large models are currently taking still. The NVIDIA's large model and Huawei's large model and WuDao, I know all upsample their data as the G2E3. So it's definitely unclear and kind of up for debate what the best approach is. Our data set, though, is basically organized into categories of things that we thought would be important for language models to know. We have a very large subset of it, which has a lot of academic information, mostly academic preprints, philosophy, health, archive, medicine. It has patent information, and it has a data set of US legal texts. This is kind of probably the biggest difference between our data set and the one that G2E3 was trained on. We really wanted to promote the ability to learn factual information. And so we tried to put as much factual information into it as we could. There's also some internet scrapes. So we have a processed version of Common Crawl. We have Open Web Text 2, which is a replication of Open Web Text, the commonly used data set. We scrape Stack Exchange and we scrape Wikipedia. We also have a data set. We also have a large number of books, various data sets involving dialogue. A lot of the applications people want to use these models for involve some kind of interaction and some kind of conversation. And so giving it dialogue structured data is conjectured to be important for that. And then there were some miscellaneous things that we wanted our model to have a better understanding of than it would by default. And the big things here are code and mathematics. So DM Mathematics is a data set produced by DeepMind, which is just a whole bunch of math equations. And GitHub is GitHub. So we fed it a lot of data on code, and we fed it a lot of data on arithmetic in the hopes of improving performance on each of those. And as I'll talk about in a little bit, it seems like that kind of paid off. Oops, didn't quite fix all the sorry, I'm not very good at this. So this is probably the point where I want to minimize my slides and pull up the preprint to talk about the model that we actually trained. We followed a largely standard approach to training this model. The architecture is approximately the same thing as GTB3, as GTB2, but there are a couple key differences. So the first key difference is this thing called rotary positional embeddings, which are a special kind of positional embedding that was invented by a Chinese research group that our experiments have shown are pretty effective. And kind of the idea is that they are an improvement on sinusoidal embeddings. In sinusoidal embeddings, you add the sinusoidal component to the vector, and here we're multiplying by it. And what multiplying by it does is instead of just basically appending a additive component, what we're actually doing is taking the embedding vector and rotating it in space. So that the embedding vector, its orientation, tells you what position in the data set it was. And this is something that the importance of positional embeddings is up for debate and depends on exactly how you want to structure your experiments. But we found that this generally gives a 5 to 10% boost in performance, so that seems pretty worthwhile. We also did our attention and feed forward layers in parallel. So the standard picture, so this right here is the standard picture for how it works. You do the attention, you have the residual, you do the feed forward, and you recombine the residual again. And what we did was we took the second component and just did it in parallel. So we had, I thought I had made a diagram of this, but I apparently did not. My apologies. We have an equation now. We have an equation. We do not have an equation. Okay, so instead of, there we go. Instead of doing these two components sequentially, we did them in parallel. So we have the residual stream, we have the attention stream, and we have a third stream here for the feed forward, and then we combine them all together. And this is conceptually not very different from what a transformer is doing anyway, but it decreases the amount of message passing you need to do within your GPUs. And so we've been able to see a speed increase. And that is a pretty cool innovation that was created by one of our members named Ben Wang, who more or less single-handedly created and trained the GTP-J 6 billion parameter model that we released over the summer. And we did some, we used some different initializations, but that is largely speaking how we ended up designing our model. There we go. And then we trained our model, and the final important component is, of course, evaluating our model. So let me zoom out a little bit. So our preprint has a lot of plots, and this failed to build correctly. That is frustrating. Why did that happen? My apologies. I
don't know. That's an excellent question. I don't know. I think it might just be the version on Overleaf. I don't know. It's like, I know the one on BMKSH is working correctly.
Okay, that was Eric Pelahan, one of the authors of the paper who just chimed in. I was 90% sure that that was the version that we submitted to the Big Science Research Workshop on training large language models.
No, that's the original. That's closer to the original version. That's not the ACL version. No.
That explains why I didn't have the diagrams I thought it was going to have.
Yeah.
I compiled the wrong version to show you guys. My apologies. So, oh yeah, no, that makes sense. We reorganized the file structure and moved kind of the diagrams around because I wanted to change the plots. All right, so apparently this is going to take a bit of time to compile because there is a very large number of plots in this. But we spent a lot of time working on figuring out how to best evaluate our model. And evaluating language models is extremely tricky. This is another thing that I think there's a growing awareness of, but at least when we were getting started, there was very little conversation about, which is that the exact way that you evaluate your model can significantly change its performance, down to things that humans don't even notice in the code base can have pretty big impacts. So one thing that's been very important to us is developing open source frameworks and open source code bases that people can use to do things comparably. And so we've been building a language model evaluation framework called the Language Model Evaluation Harness. Here we go. That we went and we implemented a whole bunch. There's like about 150 now. Yeah, this is more what I was anticipating. Cool. There's about 150 now evaluations implemented, and it's been really useful for making fair and making real comparable results to other models. We have found that even when we believe very strongly that we've implemented things exactly the same way as other people, the results come out a little bit differently. And that's probably because of the extent to which the exact wording and the exact presentation and the exact option presentation are done has a very large impact on language models. And this is kind of a big topic in current research. So evaluating things consistently is difficult. So we compared our model to the FAIR-seq sequence of models, which is some models put out by Meta AI, well, while our training was actually going on. So at the time we started training this, the largest English publicly available model, like G2B3 style decoder model, was the G2BJ 6 billion parameter model that we had released. And by the time we finished training, it was the FAIR-seq model.
Asterisk on the Megatron 11B model that we don't talk about because it was probably undertrained.
Okay.
So
yes, there's another model that I'm ignoring because it doesn't really work. But it is larger than it is 11 billion parameters, but whatever. So we compared to the FAIR-seq models, which are publicly available. I think this is a really great thing that Meta did. They released 1, 2, 3, 4, 5. They released 6 dense models as well as 4 mixture of expert models. So mixture of experts is not really something I'm going to go into too much detail about, but something that large tech companies are excited about because it lets you trade size for compute. At the cost of having a much physically larger model, it takes less compute to get to the same level of performance. And kind of the way they achieve this is that it's not, in a sense, fully utilizing all of its parameters. They are extremely sparse. And for each computation, only some of the parameters are being used. And there's, so we compared those exclusively to the dense models because comparing to mixture of expert models is difficult. So in all of these plots, you see parameters along the x-axis and accuracy in score accuracy along the y-axis. So we did a bunch of language modeling tasks. We also did measuring massive multitask language understanding, which is a very interesting data set by Dan Hendricks that compiles some pretty hard questions. And a lot of them are academically oriented. And we were very pleased to see that our model significantly outperformed both the FAIR-seq model and G2B3. And we largely ascribe that to the fact that we included in our training data the kinds of factual information about law, about medicine, about mathematics, about chemistry that this evaluation standard uses. And we also did some arithmetic evaluations. So the accuracy numbers here are extremely small, but this is a evaluation set that is typically fine-tuned on, and we didn't have the computing resources to fine-tune the FearSeek model or the money to pay OpenAI to fine-tune their models for us. So we ended up doing a zero-shot comparison on this. So the scores are very low, but the relative score is high. If we go into the appendix, we have arithmetic problems somewhere. More measuring multitasking understanding. We do not have arithmetic. Okay. I have arithmetic results that I need to add to this draft. I apologize about that. But we have arithmetic results that are consistent with the improvement in performance here. And that's something I'm really excited about because, sorry, the improvement, screen glitch there, the improvement here. And that's something I'm really excited about because the extent to which things that quote unquote naturally make sense to transfer between different evaluation standards don't always do so. So just because we're good at these kinds of math problems doesn't actually mean that our model is going to be good at arithmetic. But we've been able to see that at least in kind of more academic related subjects, that knowledge of the same domain does tend to, that our model performs similarly well in the same domain. And that's very exciting. So I want to talk briefly about, what time is that? All right, cool. All right, I want to talk briefly about safety and why we are releasing large language models, and then kind of field any questions that people have. So one of the big questions we get is why release a large language model in the first place? If you go read the original announcement of GPT-3, they are very concerned about the bad things people could do with their language models, and that is the stated justification for why they didn't publicly release it, as well as for why for a very long time they didn't even let anyone pay them money to use it. You had to apply, you had to get approved. They read over your research statement and what you were going to do with it, and they were very strict about kicking people off if they did things they didn't approve of. And there are 2 or 3 main reasons that we think that releasing these models is good. First, and most importantly, there are important pieces of research on how to use models safely that can only be done if you actually have access to the models. You can do theoretical work, you can do smaller scale work, but what we've seen is that larger models can have suddenly emergent abilities that don't show up at smaller scales. And that if you really want to evaluate how to interact safely with large models, you need to actually be working with large models. And the other really important thing is that most of the harm done by GPT-3 was done the day it was announced. In the ML community, it is very popular to talk about how extraordinarily expensive and inaccessible these models are. And there's a sense in which that's true. There is a sense in which these models are extremely expensive. They do cost millions. It costs millions of dollars to train GPT-3. If I wanted to go train GPT-3 tomorrow, it would cost me about $6 million based on my computing estimates. And that's a lot of money. It's not something that most universities have readily available. But it is something that is, in the grand scheme of things, for governments and for companies, not that big a deal. It is like 1% of, so Microsoft's recent language model, which is currently the largest dense language model in the world at 530 billion parameters, costs like 1% of their annual research budget. If you look at governments, the US government, for example, has an operating budget in which the cost of training a dozen GPT-3s is a rounding error so small it doesn't even show up. I don't know what the government of Sweden's budget is, but I imagine that you don't have to be a country as large or as wealthy as the United States for this to ultimately be not that much money if you really wanted to invest them. And so far, the main detractor for why these models haven't been trained by governments and haven't been funded by international organizations is less ultimately about actually getting the cash together and more about having the political will to spend the money. If the US government, if the Swedish government, if wanted to train a 100 billion parameter language model, they could just go do that. And if a large company wanted to train one of these models, they could just go do that. It's a matter of whether they think that's a worthwhile use of their resources. So for that reason, we think that most of the harm done by GPT-3, whatever it was done the day it was announced. When people started to realize that you could simply pump money into these models and pump compute into these models to get much better results, that the information that was the case was the thing that could potentially be worth hiding from the world. Once that information is out there, many countries, many companies could easily afford to build these models. And we see this in my large chart where you have Microsoft, DeepMind, Baidu, EleutherAI Research is a AI company in China. Nivre is the largest AI company in Korea. Huawei, AI21 Labs is a very well funded startup in Israel. OpenAI, Google, Anthropic is a recent startup that was basically a splinter group from OpenAI. In the past 6 months, these groups decided it was worth spending money on training these models, and they trained a large number of very large models. 530 billion parameters. It's 4 times the size, 3.5 times the size of GPT-3. So the money is there. The resources are there. The harm, an individual's ability to access these models is not, in my mind, the make or break for the ethical use of this technology. If you look at the history of unethical technology applications, overwhelmingly it's done by governments, it's done by companies. It's not done by academics, it's not done by random people on the internet. And so I think that if we're going to say this technology is really dangerous, so it's important that only the powerful governments and wealthy companies have the ability to access them, you've kind of set yourself up for failure in terms of making things safe for everyone. And that's kind of one of the biggest reasons to do this, because and that's really one of the biggest reasons to do this. And people can do very good and important research using these models. So there have been a couple really great papers I want to highlight that used our models and our data. The data part here is pretty important because there's a lot of research you can only do if you actually have access to the data. So you can pay OpenAI and get access to their model. You can't get access to the data set GPT-3 was trained on now. So there were these are papers on language model security and memorization. And there's a really interesting paper on the extent to which language models can do generalized reasoning that came out recently. And all of these papers use our models and use our data set, and several of them explicitly state that the research that they were doing would not have been possible if we hadn't trained the models we did and released them in the data sets in the way that we did. And that's something that I think is just extremely important to the scientific community at large, because it's important that people are able to take these models and study them. If we're going to have, as a society, as an international society, kind of the conversations that we want to have about the ethical applications of these technologies, at a bare minimum, we need to know what they do. We need to know what their limitations are. And if we're reliant on the large tech companies to spend millions of dollars to develop them and then study them themselves and tell us how they work and tell us what their limitations are, I don't think that that's a good way to advance the conversation. And so putting these models in the hands of researchers like yourselves, putting these models in the hands of people who want to play with them and break them and figure out the ways in which they suck is really important in order to have the information out there so we can, in the first place, have the conversation about the ethical application of this technology. Yeah, so briefly, kind of what's next for myself and for EleutherAI. So EleutherAI has grown substantially in the past year. We have more than 24 active researchers who are working on a bunch of different things. But kind of an overview of what I'm interested in is, so first of all, Pythia is a suite I am currently working on building, which is going to cap out at GPT-NeoX 20B, but it's going to be a variety of models of different sizes. So it's similar to the paper, like the scaling laws papers on language models, but all of the models are going to be publicly released, and all of the checkpoints, partially trained checkpoints, are going to be publicly released. And I'm really hoping that this will enable people to do research on how things change across scale that was simply not really possible to do before, because you can make a data set of large language models. You can take GPT-Neo, you can take GPT-J, you can take GPT-NeoX. Yes, we have been changing our names every single time we've released a model. We're hopefully going to stop that for now. You can take models trained by other people, like the AI suite of models in Swedish, so it's probably not a great comparison. You can take models trained by Stanford, you can take models trained by other organizations and build a suite, but there's a lot of uncontrolled variables across these. And so I think that putting together a systematic suite of models at different scales is going to enable people to do really good research. Access to compute for researchers is something that we are currently working on. We're applying to some grants, and we're going to try to make using these models accessible to people. If you want to use GPT-NeoX and you do not have the computational power to run this model, which is very reasonable because it takes like a pair of 3090s or an A6000 to even load the model in the first place. But if you want to do research that requires doing inference with our model, and you just don't have the resources to do that, please email me. We have compute, and we are working on making it available to people. But we want to put the models, and we want to put the ability to analyze the models in your hands. And we would love to talk to you about how we can make that happen. I personally am excited to, once I train more models, do scientific research on them. For me, one of the big draws of this was that I was interested in scientific questions and ethical questions that couldn't be answered with what was at the time the publicly accessible language models. And so I went and said, I'm going to train large language models so that I can do research that interests me on them. So I'm excited to do that. And multimodal models is one of the biggest things in NLP today, especially dual image and text models. And so that's definitely an area where a lot of people at EleutherAI are currently working on stuff like DALL-E and Glide, as well as on novel things. I also want to give a quick shout out to Aleph Alpha, which is a research group in Germany that recently released a model called Magma that is really, really cool. They took GPT-NeoX and they used adapters to turn it into a multimodal model.
They will be on the seminar in a few weeks' time talking about that.
Excellent. Yeah, so they released the model yesterday. The paper has been out for 5 months, but they released the model yesterday, and I'm very excited about that. And finally, multinational and multi-organizational collaborations. Magnus mentioned at the beginning that we've been talking to them about both giving advice as well as collaborating explicitly. We've also been talking with Mila, a research group in Canada. Many of our members are part of the Big Science Research Organization. And so we've built up a lot of knowledge and expertise about using these models, and we're very excited to share them with other people, both in terms of the products, but also in terms of that knowledge and expertise. We want to figure out how we can best enable people to train the models that they want to train. And that's really what I have. Happy to field any questions people have. I can answer many technical questions. Eric can maybe help me with some of the ones I don't know, because he's more of a hardware person than I am. And I'm, would love to answer any scientific questions you have for sure. So why don't we open this up to the floor?